if you've got three pegs that are stretching out a piece of rope or string or what have you that's 30 inches long in total, what's the optimal way to find or how do you find the largest area? All right, so I might as well recap since I'm here. Um, so I was just kind of playing around with this and thinking, if I stretch this out a bit and assume that A is going to be a fixed point, B is going to be a variable distance, which I can slide back and forth, but for the sake of simplicity, it's only going to slide back and forth. It's not going to be like turning and rotating around. It's just going to be moving in a straight line. Realistically, if it's going in any direction, I can just call that the straight flat line, and then C itself will be able to be rotated around a bit. It's not quite a circle. It's an ellipse, right. Okay, so C is on the outside of an ellipse based on foci A and B. And again, I assume that we get a variable distance here. I'm going to assume, I think it's right, that as you begin to shift away from the apex, AC and BC are going to be equal to make the largest area. If that's not true, then as you start shifting away from the apex, one of them is going to start getting smaller and the other one's going to start getting larger. So the area in theory should be getting shorter because the height is going to be getting smaller, whereas at the same time the base is going to stay fixed. So 1/2 base times height, your base is always going to be the same, whatever distance that is, again, between foci. And the apex is, I'm just realizing this is cool. The apex here is going to be the point along the semi-minor axis of the ellipse, where it's going to be at its peak, at its highest point. So that's where you get the same base, largest height that you possibly can. All right, so that's going to be here and here. I'm really surprised that there are this many people here. So hi, welcome. Right. So we're going to get our semi-minor axis here. And again, this could, in theory, create an ellipse. Going around like that. Forgive the drawing, I'm definitely not an artist. So whatever distance this is apart, what's really the important part is that these two are going to be the same length, so it's going to be an isosceles triangle at its maximum area. So based on that, I said, okay, if it's an isosceles triangle, we're going to get a plus b plus x is going to be 30. X is the distance between a and b are going to be the distances along the sides. And a equals b because it's going to be isosceles, so knock out that each a and b again are going to be 15 minus x over 2. If you draw a straight line down, it's totally a straight line. That's going to split x into two pieces because, again, it's an isosceles triangle. When you draw an altitude, it's going to split the other side in half. Let me make sure that if y'all are chatting, I'm actually getting an answer here, or getting you an answer, because I totally don't see anyone talking. So if you are, I apologize. Anyway, once I got that, we now have two right triangles, and you can use the Pythagorean theorem to figure out what the height's going to be. So height squared is going to be equal to 15 minus x over 2 squared minus x over 2 squared. The x over 2 terms on each of these become x squared over 4. One's positive, one's negative, so they subtract out. and you're left with h squared is equal to 225 minus 15x. There we go. And so h is going to be the square root of that. And we can plug that into the area formula. So area of the full triangle is going to be 1/2 x times height. And then we sub in the square root for h. And now we're working all this stuff down. This is a weird maybe thing that I learned in gosh, I think my calculus teacher was really the first one to do it back in high school. So he liked to factor out the term that has the negative exponent so that it will increase the exponent of the thing that has a positive exponent. So here, if you factor out a 225 minus 15x raised to the negative 1/2, this is going to cause the first term to become that thing raised to the first power because you are subtracting a negative exponent, so it's adding a half. All right, so 225 minus 15x is going to be here. We pulled out the 1/2 from the first term. We pulled out the square root, or negative version of the square root. So that's what's left here. And then in the second one, we pull out a half, and 225 minus 15x to the negative 1/2, and then we're left with half x. Okay. Right, so now, related rates, we're going to take dA dx. Okay, so technically we don't know it's a maximum, but we totally know it's a maximum, right? It's what we were going for. This could, in theory, be a minimum, but you just want to, keep that in mind. Again, we know it's going to be a maximum because we just did this diagram over here, and the height's only going to get shorter if you go off to the side. So, yeah, it's going to have to be a maximum. So if we let this be equal to 0, yeah, we got enough room there. This is going to be 0 equals 1/2 times 225 minus 15x raised to the negative 1/2. Alright, and I'm going to just jump to, it's just kind of skipping a step, so like you wouldn't want to do this on your homework or anything, but we're going to say here, because this is multiplication, we're setting it equal to 0. Either the first term has to be 0 or the second term has to be 0. Alright, that second term there is going to be 225 minus 14.5x. And first term is going to be this one here. This one is, because it's a negative exponent, it's going to be in the denominator. So this can't be 0. This is a 1 over a set equal 1 over 0 set equal to a, whatever. 1 over a set equal to 0. And then, like I said, you just can't get that. I shouldn't do a, because we already did a. We'll do q, because that's close enough. Alright. So 1 over q is equal to 0. Q can't be anything. So, oh well. Alright, which leaves us this part here. So that's going to be 225. Is going to be set equal to 14.5 x. So that's going to be 29 halves. So if we multiply 225 by 2/29. That's going to be our x value. It's going to be 450 over 29. And it looks like this is going to be somewhere about 15.517 inches. Alright, so this was string is going to be 30 inches long going around all three pegs. So it looks like the base at least is going to be 15.5 inches, again, give or take. And then the other two are going to be 30 minus. That should be a minus answer. And divide by 2. So each of the other ones should be 7.24124. Yeah, 1. Generally speaking, I'm not going to be quite that I don't know exactly what I'm saying here. I'm not going to be that sloppy with this and stuff like that. I'm probably just going to round off, make it 15.5 and 7.2 inches each for the sides. It does round all three of them down, so technically it's not quite right, but yeah, whatever. Alright. Anybody have any others that they want to look at? So I'm working off of a list, but so Soul Reaver, if you're here, I'm going to be working. I'm going to pull number 7 because, like, even though you weren't asked to do, or you didn't decide to do that one, or maybe you already figured it out yourself. Sure, why not, right? No. All right, whatever. Alright, so find the smallest square inscribed inside of another square such that each corner of the smaller square... Oh, right, no, that's what inscribed means, so... Alright, so find the smallest square that can be inscribed inside of another square. Alright, so if we just look at it, right, you can't have anything that's going to be like... You can't really have anything that's like this. Because that is not actually going to be a square. each corner of the small square touches a side of the larger square. So, I mean, the only actual picture that you can draw of a square inscribed in another square, I thought, was going to be where it's all at the centers. That can't be right. I think the Mathologer symbol is diagonal too, so isn't 100%. Yeah, okay, so it is slightly off. No, okay, so this does work. All right, so if you have, side length A, whatever it's going to be, then you want to know, this is the X that we want. What's the smallest square we can make? So the side length is going to be X. It's going to be the same all the way around the other square. So all of these little pieces are going to be the same as each other. All right, let's do M and N here. This is going to be M. This is going to be N. This is going to be M. N. M. N. Provided, of course, that you do draw this pretty well. My drawing is terrible. Alright, so all these are right angles. Alright, so how much of this do we actually need? So this is going to be like an interesting practice in like what to pay attention to and what not to pay attention to. All right, so here we know that M and N are going to add up to A. And that we've got a Pythagorean relationship. So it's going to be m squared plus n squared equals a squared. No, that's not a squared, sorry, x squared. Phew. I do teach this stuff, I promise. Alright, so we can get one of these in terms of the other. And it's arbitrary which one we pick. So m equals a minus n, which means that over here we can change this to m squared is a minus n squared plus n squared equals x squared. Alright, so we can expand this out, and again, no, not with this one. Okay, this is actually going to reinforce. So this is going to be a squared minus 2an plus n squared again is equal to x squared. a squared minus 2an plus 2n squared equals x squared. Alright, if I like try to replace x squared with m plus m squared plus n squared or anything like that, it's just going to come out to be an identity, so that's not going to help. Alright. At this point, we could try to derive. M and n are based on each other, so we could base it on how big x is. A is a constant, so that's going to get wiped out. A here is a constant, so it's just going to hang around with the 2. Sure, why not? So if we take the derivative of this entire line with respect to x, technically that's poor notation, by the way. I wouldn't do that. Alright, so ddx on the left, ddx on the right. There's got to be another relationship that we can use here. So I don't think it's just as easy as that. Anyway, we were going to wipe out a, so a is constant. X is the target to minimize. So we're going to get 0 here minus 2a dn dx plus 4n dn dx equals, oh, wait. No, okay, we don't want that. So we want the okay, so we can kind of go 2 ways with this. Since x is the target to minimize, we don't want to derive based on it. So what are we changing that's going to forcibly change x? So in theory, we could say, well, like, we're changing n. Another option would be we're trying to find the smallest square, so we could say, okay, smallest square measured by area, and then we could do the same thing with that. So we'd be trying to find, like, x squared is the area. Well, this is the area. Y'all can backseat if you want. Yeah. Alternatively, there's only one viewer here, and it's me, so it's alright, you know what? Yeah, let's make this a of the smaller. And that way we're just minimizing the area. In the case of a square, right, whether you're minimizing the area or you're minimizing the side length, it's not going to matter, it's the same thing. So we can do ddn. So ddn of the left and ddn of the right is going to get us, this is going to do the same thing as we had before. It's just now not going to give us the derivative terms on the left. So that's actually very convenient. ddn of a squared is nothing, so that's 0. ddn of negative 2an is going to be a negative 2a. ddn of 2n squared is going to be 4n. Equals, and then over here, ddn of the area is going to be an unknown dadn, but we're trying to set that equal to 0 because we're trying to minimize it. Alright, I'm just going to put a scribble there. We know that that says smaller. Totally says smaller. It's cool. Alright, so it's set equal to 0, and this says that the relationship between n and a is now 4n equals 2a, if we bring that over. Or 2n equals a. Alright, so then n has to be halfway along each of the sides. It's totally a square. N and n, making up each a. Okay, cool. Alright, so I got another one that says inside a given cone, the height of which is, oh no, inscribe inside of a given cone, the height of which is equal to the radius of the base. So this is way too big. Alright, so R here and R here. Inscribe a cylinder whose volume is maximized, or whose lateral area is maximized, or whose total surface area is maximized. Alright. If you can draw a decent picture, this is your first step, quite honestly. I wish I could do a smaller E. Sure, why not? Yeah, I wish I could have a smaller eraser for this. Be nice. Nope. Alright. So this is going to have radius of the cylinder and a height of the cylinder. Hey. I was just doing number 7 because I thought it was an interesting. Don't worry too much. So I was talking about number 4 earlier. There we go. So like I was just playing around with this because I was like, I don't even know necessarily how to approach this at first. And then I was like, okay, fix one of your points. And then the next one, we can say it's anywhere out in space, but the easiest way to say it is just like move it horizontally. Right? And then if you move this point, it's just going to move horizontally back and forth toward or away from A. So that's going to make A to B. And then I was playing with this and I'm like, how do I, like, what describes C? And I suddenly remembered, oh, this is the same as making an ellipse with foci A and B. So now you've got an ellipse with foci at A and B. Well, this means that the maximum height, the maximum area is going to be found with, given a fixed base, the place where you're going to be at the maximum height is going to be when these two things are equal to each other. And if you think about it in terms of making an ellipse, it makes complete sense. Because if you start tilting to one side or to the other, then one of them is going to get shorter and it's going to start dragging it down. So then the 1/2 base times height being your being the equation that we're working off of, right? 1/2 base times height, the height's going to shrink, so the area is going to shrink. So you got to like maximize the height, really, is what we're doing here. Given a fixed base, we'll just call it x. So then working out a whole bunch of stuff over here, this was like, what do we get if we fix that base at x? What's the relationship between the three sides of the whole triangle? So we get this based on the 30-inch total between all three. And then we said, what's the height? Well, that's going to be a Pythagorean theorem due to the fact that you're dropping an altitude down, and it's an isosceles triangle. So then this went through a whole bunch of stuff. And then that gets dropped into the 1/2 x times height now is going to be that. And then you can derive. So doing all this derivation, this is factoring out 1/2 the square root, or 1 over. Technically, if you think about all of it together, it's 1 over twice the square root term. And I'm just factoring all that out. And it takes out the half here. It also makes the first term, which was a square root, become just a whole 225 minus 15x. The second part is 1/2 x times the stuff that was factored out. So that's gone. And that's here. Max, or technically minimum, but we know it's a maximum, when dA dx is 0. So you say, okay, either the first term or the second term is going to be 0 because you got multiplication here. And their product is equal to 0. First one can't be 0 because you've got 1 over something equals 0. So that doesn't make any sense. And the other one, when you do that out, x ends up being 15.5 roughly. And then the sides of the isosceles triangles are going to be about 7.25. Pretty close. So I was explaining it. I don't know who else is technically here. Yeah. I think it's just you and my viewer account. So. So I was like, well, let's do 7 here, because this is just kind of a fun exercise to think about. I kind of knew intuitively that this was the answer, and then it was a matter of proving it. So if you want to inscribe a square inside of another square, the smallest area is going to be when its corners are halfway across the other square sides. That's alright. I got VOD too. Oh, unless I'm skipping. My audio is fine, right? No, that's not it. Oh. Don't use your data on me, man. Is my audio skipping too? No? Okay. Alright, well. Good/bad news. My phone isn't skipping, so. So anyway, this was kind of a fun little Okay. Yeah. So it was a fun little proof here. 8. Yeah. I was looking at number 8 here. This was going to be fun. So you got like 3 different optimizations you want to work on. So one was max volume, 2 was max lateral, and 3 was max total surface area. So like 1, you just basically at this point it just becomes a matter of, do you remember the formulas? And what are the restrictions on the cylinder based on the cone? Alright, so Oh, It's the volume of the cylinder. It's going to be pi RC squared times HC. Why am I using C? Right, CY. C doesn't make any difference here. Right, it's a cone and it's a cylinder. That's not crowded at all. Alright, so yeah, there's a relationship that must exist. There's a relationship that must exist between the cylinder and the cone. It's here. Think about the point that lies on the... Really? Okay, I guess the blue is in the foreground no matter what. So there's always going to be a point on these outer edges of the cone which are going to follow the... Yep. Which are going to have a slope of 1. So because the radius of the cone and the height of the cone are the same, there's the slope of the sides is always going to be 1. So that means that we can... Punk. Yeah. Maybe I was there for a little bit too. Unless I just stopped moving. Alright. So yeah, the slope of the cone is always going to be 1 here. Then what we got is that so the line equation is then going to be y equals, let's not do y. This is going to be the height of the cylinder is going to be equal to why, thank you. So the height of the cylinder is always going to be I mean, this is y equals x plus 1, but now you got to think about what are y and what are x. So x is going to be the radius of the cylinder. Goes the other way though. I think the maximum area of your square can be when it's all... No, I mean can be when it's literally equivalent, when one of them is 0 and the other is 1. So m and n are... One of them is going to be 0, one of them is going to be 1, so literally it is the same square as the original. Or so like m equals a or n equals a would be the maximum. This is going to be the minimum. So the height of the cylinder is going to be 1 minus the radius of the cylinder. I think should be the case. So if your radius of the cylinder is very small, the height of the cylinder is going to be very large. It's almost going to be equal to the radius of the cone. Yeah, okay. With bounds, radius of the cylinder is going to be less than r but greater than 0. And the height of the cylinder is going to be the same. So between 0 and the radius of the cone. Alright, they got sort of an inverse relationship working there. Sorry, ever so often I just gotta check because I'm getting really paranoid. See if I'm skipping, because if I'm skipping, then everybody else is going to be skipping. But I'm just not seeing it. It's weird. Alright, so the radius of the cylinder squared times the height of the cylinder is going to be equal to 1 minus the radius of the cylinder. It's not 1. It's not 1. Sorry. That should be the radius of the cone. Alright, radius of the cone is going to be constant. Radius of the cylinder is going to be variable. So let me get the volume of the cylinder here. Now we only have one variable. Alright, so that's going to work here. So we want dV cylinder over dR cylinder. It's going to be equal to, and now we got a product rule here. Probably separate it out, do distribution. So this is going to be pi r cylinder squared r cone minus, sorry, r cylinder cubed. I don't know what's going on. So when we take the derivative of these terms, the radius of the cylinder is going to be variable. The radius of the cone is going to be constant. So that's just going to be pi r cone times 2r cylinder minus 3 pi r cylinder squared. And then dVdr is going to be 0, again to maximize the volume. We get 0 equals, we got 1 pi and 1 radius of the cylinder. Alright, so that leaves then 2 times the radius of the cone minus 3 radius of the cylinder. And then here again we got this multiplication going on. So the pi radius cylinder could be 0, but then the radius of the cylinder would be 0. So that's not going to help. That's essentially minimizing. Alright, so pi r cylinder equals 0, which again doesn't really help. Or 2r cone minus 3r cylinder equals 0. Shift over, so 3r cylinder equals 2r cone. So r cylinder is equal to 2/3 r cone. So if the radius of the cylinder is 2/3 the radius of the cone, that's when we're going to have a maximized volume. Alright, for 2, you want the maximum lateral area. The lateral area is just the part that's around the outside. So this is going to be area lateral. It's going to be stupid thing. That's why I need wireless headphones, right? I hate the amount of batteries that this other stuff would need. Alright, so the area, lateral area, and I'm right on the edge, okay. So okay. Alright, so the lateral area is going to be, it's a rectangle whose width is going to be the height of the cylinder. So height of the cylinder multiplied by the circumference of the circle. So this is going to be pi times the diameter, or 2 pi radius of the cylinder. And again, we want the same thing that we did before. We only want one variable. So this is going to come into play again. The height of the cylinder is going to be equal to r cone minus r cylinder times 2 pi radius of the cylinder. So multiply that in. It's going to be 2 pi r cone r cylinder minus 2 pi r cylinder squared. Alright, so then we want to figure out again, if we want the maximum lateral area, we've got to take dA dr cylinder equals 0, and that's going to be equal to, here, this is going to be 2 pi radius of the cone minus, here we get 4 pi radius of the cylinder. Alright, so then that kicks over. We get 4 pi radius of the cylinder equals 2 pi radius of the cone. And divide by 4 pi. We get the radius of the cylinder is going to be equal to 1/2 radius of the cone. Nice. Alright, so then 3, the maximum, if we want to maximize the total surface area of the cylinder, then again, that's the same thing. Area of the cylinder in total is going to be equal to the same lateral area, so height of the cylinder times 2 pi r cylinder plus the 2 caps. So this is pi r squared, 2 pi r cylinder squared. And again, we need to trade out h cylinder for the same thing we had here, radius of the cone minus radius of the cylinder. Times 2 pi r cylinder plus 2 pi r cylinder squared. Alright, and then we want dA dr cylinder to be equal to 0, which again, then we're going to take the same. Really? Okay. Well, that seems to be easier. We're going to back up a little bit. Let's simplify this. So 2 pi r cylinder multiplies into 2 pi r cylinder r cone minus 2 pi r cylinder squared. And then plus 2 pi r cylinder squared. Okay. So these two terms are 0. Works for me. Alright, so those are out. Just going to check something real quick here. Alright, coming back to it. So, with this, dA dr cylinder is equal to 2 pi r cylinder r cone. So we're going to be r cone, 2 pi, those are all constant. We're just going to be taking the derivative of r cylinder, so that's gone. So that's just going to be 2 pi r cone. Oh, that's not good. Alright, so I screwed up something. What did I screw up? Alright, there has to be two terms here. That's not good. Because if this is 0, then that's going to mean that we got 0 for the radius of the cone. So clearly this is false. Okay, I gotta back this up then. Alright, so the height of the cylinder times 2 pi r cylinder. Height of the cylinder times 2 pi r of the cylinder is going to be 1 loop around pi times the diameter, right? So we're good. Hopefully I didn't bin this whole thing, so plus pi r squared for the top and pi r squared for the bottom. So that's 2 pi r squared. It's the radius of the cylinder that we're using here for the caps. So that should be those two. Now you all get to watch a mathematician panic. This is the sort of thing that happens in my class every so often, where I just realize, like, oh no, I don't, I didn't see this in my notes. This didn't happen when I was practicing. All right, total surface area of the cylinder. So you get pi r squared for the top because it's a circle, pi r squared for the bottom because it's a circle. So pi r squared for the cylinder is going to be there. Then we add the height of the cylinder times 2 pi times the radius. Why isn't this working? Again, any backseaters out there, feel free. Oh man, why isn't this working? All right, let's just reset. Nope, can't go back any further. All right, cool. Oops. I hit my. I hit something on my pen or something. Anyway, not working. Cool. Let's just erase this and go back. Alright, I am getting a little bit of a stutter here. But it's not with me, it's just with my pen. Okay. Alright, it could just be as simple as saying that, well, the height of the cylinder should be equal to the radius of the cylinder. Somebody's probably screaming at home going, yes. Well, now I'm curious. So if this was if this is true, if the radius of the cylinder is equal to the height of the cylinder as well, because the outer edge has to lie on the edge of the cone, whose height and radius also have to be the same. Yeah, I think that's right. So this could be equal to pi r cylinder squared times r cylinder, so pi r cylinder cubed. This could be much easier. Oh no, because then we get the problem that we had on the other one too. So this is going to mean that For this particular case, if we use this particular setup, DVDR is going to be 3 pi r cylinder squared, which equals 0, which means that the radius has to be 0. Okay, so we're getting the same problem here that we did on the other one, but that's actually good news, I think. So I think that this means that now we just have to tweak the formula that we had for number 3 and reverse it. So instead of concentrating on r cylinder equals height of the cylinder, or instead of doing the height of the cylinder is radius of the cone minus radius of the cylinder, now we're going to use this other one here. So let's try it again. So this is the total area for the cylinder. It's going to be equal to 2 pi r cylinder squared plus lateral area, which we had in the previous one, was height of the cylinder times 2 pi r cylinder. Okay, so now in this case, we're going to say that the height of the cylinder is going to be equal to the radius of the cylinder. Now we should get two different... Nope. Okay, all right. Two pi r cylinder squared plus. If this is r cylinder, then this is 2 pi r cylinder squared as well. So now we get 4 pi r cylinder squared equals... equals AT, a total, which then derived is not going to get us two different terms. Okay. Okay. So I'm wondering, Soul Reaver, is this the problem you had? Oh man. All right. All right. I'm going to take a break. Enjoy the madness for a bit. Alright, had to think about it. Didn't really help. So... No! That was a mistake. Alright, I'm not thinking of anything that's gonna, like, dislodge this. And that could be a potential problem. Okay, inscribe on a given cone, the height of which is equal to the radius of the base. So we got that picture. A cylinder whose total area is maximized. So that's surface area. So then we've got area of the two caps, 2 pi r squared. Alright, plus. So either we go with the radius of the cylinder has to be equal to the height of the cylinder due to the fact that its top corner is going to be on the edge of the cone. Okay, so that's going to be limited to or the height of the cylinder is subject to this condition, in which case the radius of the cone minus the radius of the cylinder is equal to the height, for the same reason. Can we bring those together? That's interesting. This one's going to say that the radius of the cone is half the size of the radius of the cylinder. Or, no. This is giving a single solution. There's only one way to inscribe it. If I bring them together. If the radius and the height have to be the same, then the height of the cylinder is going to be half that of the cone. There's only one physical solution. So that might actually be a different problem in and of itself. Yeah, because okay, never mind. Yeah. The height of the cylinder and the radius of the cylinder being the same is only going to get you the one. It's only going to get you one particular solution. Because you can make this a really squashy cylinder, but it's really wide. And the height of the cylinder would be equal to, if we're way out here, right, if we're way out here, then the height of the cylinder would just be the complement to the radius to get the radius of the cone. Okay, yeah, alright. So then the radius of the cone, well, literally, right, the radius of the cone, nope, the radius of the cylinder plus the radius of the, nope, one of those. The height of the cylinder plus the height of the, man, height of the cylinder plus the radius of the cylinder is going to be equal to the radius of the cone. Okay, that's this. So we're okay now. This doesn't make any sense, so we got to get rid of that. So 2 pi r cylinder squared plus 2 pi r cylinder times r cone minus r cylinder. Two pi r cylinder squared plus 2 pi r cylinder r cone minus 2 pi. Is it though? Is this really how it's going to go? Oh man. R cylinder squared, which then is the same as this, so those are going to go away. You only got one term left. So we're still getting a 0 here. If we're going to have 0 for our dA, then that's going to get rid of the radius of the cylinder entirely. What are we doing? Alright. Desperate times. I don't think this is going to work. We can try. Why is this skipping? Alright, so we could try reversing this and making it r cone minus height of the cylinder equals the radius of the cylinder. I don't think this is going to change anything. Because algebraically, they're going to be the same. So this is going to be 2 pi r cone minus h cylinder squared plus h cylinder times 2 pi r cone minus h cylinder. So this is 2 pi r cone squared minus 4 pi hr r cone h cylinder plus 2 pi h cylinder squared. Plus, the stuff from this one is going to be, yeah, it's going to be the same, isn't it? 2 pi r cone h cylinder minus 2 pi h cylinder squared. That doesn't entirely cancel out. Ooh. This might actually work. Alright, so reframing your variables does sometimes work. Alright, so we got 2 pi r cone squared. And there's no other terms with just r cone squared. So 2 pi r cone squared. This is a minus 4 pi r cone h cylinder. This is plus 2 pi r cone h cylinder, so this is going to be overall net minus 2 pi r cone h cylinder. Alright, and these last two terms do cancel out. Well, here's to hoping. So this is a sub t. Yeah, but now we get... No, because when we take the derivative, right, based on h cylinder, this term is going to stay, but this term is going to disappear. And then we get a 0 over here. So then now we've got this thing equals 0 again. So that... Okay. Yeah, so that didn't do anything either. All right, I didn't think it would, but, you know. So my suspicions have been confirmed. All right, what else could be going on? I had a thought a couple minutes ago, and now it's gone. So much for that. Okay, I could try doing a system of differential equations. It's not actually a system of differential. So I could try differentiating this as it is right now on the basis of our cylinder. So dA dr cylinder. And then we say this is going to be 4. Let's just get rid of that. All right, 4 pi r cylinder plus, now we got to do product rule with these. So this is going to be dH dr cylinder, h cylinder, r cylinder, times 2 pi r cylinder plus h cylinder times 2 pi. Nope, r cylinder is going to be gone because again we derived that. Okay, now if we couple this with the other equation, this should also do the same exact thing that I've been talking about where it's not going to work whatsoever. It says that dH cylinder dr cylinder is going to be equal to r cone minus r cylinder derived is going to be -1. Okay. And H cylinder is going to be equal to what we had above, R cone minus R cylinder. Alright, so this is going to be... Boy. This is going to be a -2 pi R cylinder. This is also going to be a -2 pi R cylinder, which makes a -4. Yeah, like I said, it's going to make a -4 pi R cylinder, so that's going to be gone too, and that's going to be gone too. So then we're just left with this term again, which is just 2 pi R cone equals dAdr, which is then not going to work. So I'm constantly getting that dAdr cylinder is equal to 2 pi R cone, and that's it. Okay, so this is not. Boy, for whatever reason, this is not working for me. I think probably I'm just gonna skip it. Total cylindrical area is maximized. Height times distance around is 2 pi r times the height. What am I missing, right? Yeah, alright, I'm gonna skip it. So, for whatever reason, that one's just not working on me, or for me, so we'll skip it for now. Next one was now take a sphere and basically do the same thing. So with a different equation. That's totally connected. Alright, so at least in this case we can do RS and RC. Hey, so hail UAE to 2013. Welcome to the stream. Yeah, I had a bunch of user requested questions that came from, some random calculus text. The person in general, or the guy who sent it in was is another streamer who kind of like just does a bunch of like, I'm trying to teach myself calculus, and so I've been encouraging him. Soul Reader, I know you're watching. Eventually. So yeah, we got here. Actual height of the cylinder is going to be down to here, but radius of the sphere is going to be out to there. And functionally speaking, this is technically like we could cut this into just doing a hemisphere and like half of the cylinder, because functionally it's going to be the same. It's all symmetric. So what we're doing here is we're trying to figure out, inscribing in a sphere, we need to find a cylinder whose volume is maximized, lateral area is maximized, and total area is maximized. I was having a hell of a time on the previous one, which was do the same but inside of a cone. And the cone in question had same height as it did radius. And I was having a hell of a time due to the fact that, if you want to look, why not, right? The surface area of a cylinder is going to be 2 pi r squared, because then you got both the top and bottom, and then also the rectangle that's wrapped around the outside is going to be the height of the cylinder times 2 pi r of the cylinder. And the relationship that exists is that the height of the cylinder and the radius of the cylinder, when added together, equal the height of the radius of the cone, which I guess is technically the same as the height. It doesn't matter. It's the same thing. But yeah. So the problem is that when you plug this equation into any one of these pieces, it doesn't matter which one you do, try to get it under the same stuff. The 2 pi r squared part cancels out, and then you're just left with the 2 pi r cylinder r cone, which when you derive it is just 2 pi times the r of the cone equals 0. So the radius of the cone needs to be 0, which clearly is false, because that's not how it works. So I just decided, you know what, let's just let that one go for a while. This is extra, which is something I was randomly doing on the side and failed miserably. So if you have any insights on that one, feel free. But so we shifted to, let's do the same thing on a sphere. Now the equations are going to be a bit different, so this is going to be a little more interesting. Yeah. R equals 0 clearly just doesn't work for this, so hooray. So this is 1/2 height of the cylinder. So we need to find maximum volume. Alright, so max volume of the cylinder. Here again we do the volume for the cylinder is going to be pi r cylinder squared times the height of the cylinder, full height of the cylinder. And we need to compare that to the radius of the sphere. Cylinder. Or find a relationship between the height of the cylinder and the radius of the cylinder, which, you know, depends on what you want to do here. So we've got the radius of the cylinder squared plus 1/2 height of the cylinder squared is going to be the radius of the sphere squared. Radius of the sphere is going to be a constant, so that's going to be helpful to have in there at some point. And if we can get the height of the cylinder by itself, or at least the squared term. Okay. Radius of the cylinder squared is already here. So let's leave that where it is and move this whole thing over. So radius of the cylinder squared is going to be equal to radius of the sphere squared minus 1/2 height cylinder squared. So then we can take this and plug it into here. Volume of the cylinder is equal to pi height of the cylinder times this stuff. So radius sphere squared minus, let's just change that, right? 1/4 height of the cylinder squared. So volume of the cylinder is going to be equal to pi height of the cylinder times the radius of the sphere squared minus pi over 4 height of the cylinder cubed. Alright, Now we can differentiate this on the height of the cylinder. DHC. DHC. It's going to be dVdH sub c. It's going to be equal to, this is pi, radius of the sphere squared is going to be constant, so that all comes out. Pi radius sphere squared times the, so dH is 1. Minus, here the 3 comes down, so that's 3 pi over 4 times height of the cylinder squared. Alright, and then since we wanted to maximize volume of the cylinder, this was going to be equal to 0. So now we get pi rs squared minus 3 pi over 4 hc squared. Yeah, hey, no problem. And I've got a bunch of stuff. So Wednesdays I try to do math stream, and Fridays I try to do gaming stream. This was just kind of me having some fun tonight, because one of my other stream friends came over and said, "Hey, do you mind answering some questions for me?" So, no problem. See you later. So hail. Oh, UAE is in United Arab Emirates. Or is that not right? Yeah, nice. Well, welcome. This is great how it's like, people can be all across the world and connect with this. So, welcome. Have fun with your classes, and good luck. Alright, so 3 pi over 4 hc squared is equal to pi rs squared. Yeah, you too. Alright, so then we want hc in terms of the rest of this stuff. So now we can divide out the pi, and then this is going to be 4/3. Interesting result. Nope, that's not R2. It's R sub s squared. And take the square root of both sides. So then the height of the cylinder is going to need to be, it's going to be 2 over root 3 times R sub s. I did mark this as mature audiences, so good to know that, the random music that I piped in. Oh man. Let's try, let's try classical. That's probably a bit safer. Good times. Alright, so we got a height of the cylinder is going to now have to be 2 over root 3 times the radius of the sphere. And now we also have the relationship to the radius of the cylinder. So we can plug all that into here. That's kind of gross, but whatever. This will work. Alright, so hc squared, we can plug that in. That's alright. So this was 1, maximize the volume of the cylinder. Let's come over here then. RC squared is equal to RS squared minus, this was 1/4 HC squared, which is now going to be 4/3 RS squared, 4/3 RS squared. Yep. Okay, so then we're going to divide out the 4s. So the idea was that we were trying to find the maximized volume of the cylinder that you can fit within a sphere. Um, so basically, I'm assuming that this sphere is of arbitrary constant size. So it's just all going to be the same. And then what we're doing is we're taking this cylinder and saying it could be like really, really tiny here, or then as you build it out, it's going to shift around the other side of the sphere and then get smaller again. So we want to find the one that has the maximum volume. The points are going to go around the outside of the sphere. And as this point here, for instance, starts moving around the outside of the sphere, whether one way or the other, we're going to determine how the volume changes based on how the height is going to change, which you can decide if it's the height that's actually driving it or it's the radius of the sphere or radius of the cylinder. Either one's changing. So, and they're both changing kind of the same way. So we say that dV/dH, the speed at which the volume of the cylinder changes based on the height of the cylinder changing, is going to have this relationship. So, like, if we just look at way back here, dV/dH is going to have a specific relationship to the radius and the height, but we're also constraining this to exist on a sphere. So the radius of the the radius of the cylinder squared plus half the height of the cylinder squared has to be equal to the radius of the sphere squared, which again, this was a constant. So we can feed this into the larger picture and say, okay, the height of the cylinder is going to have this particular relationship on a sphere. So the volume of the cylinder is equal to this stuff when it's on a sphere or inscribed within a sphere. Then we said, let's calculate the change in the volume compared to the change in the height. And again, we said we want the maximum volume. So, what level are you in, by the way? Just if you're still here. So, like, if you're in Calc, this is probably a bit further, or Calc 1. This is a bit further than where you are in the semester, probably, but yeah, I don't know where that is, sorry. I don't know, like the International Baccalaureate or A-level being kind of British stuff. Yeah. So could you, in theory, you could use equations of a sphere. Now the problem would be, how would you figure out what the volume of the cylinder is based on the equation for the sphere? So theoretically, right, you could do something with, oh boy, oh man, it's been a while. Oh, actually, you could make this two-dimensional. Ew. In theory, you're looking for the maximum area of a rectangle inside of a circle. Maybe. Because that's a cross-section, so that might be a little different based on the other shapes that you have around it. I think this will work inside of this particular problem. I'm going to have to do that. I'm going to do that next. So that's an interesting thought. 'Cause I think that's true, but I don't want to, like, definitely say it's true without actually proving it. Alright, so then the radius of the cylinder is going to be equal to square root of 2/3 times radius of the sphere. So the radius, or the height of the cylinder needs to be, you could say like square root of 4/3 radius of the cylinder, or 2 over root 3 radius of, radius of the sphere, or whatever else we got here. Radius of the cylinder needs to be square root of 2/3 times radius of the sphere. So now we have like dimensions for the cylinder. And again, the one that has maximum volume. Alright, good luck. I also specialize in pre-calculus. So that's like functions and trig, generally. Alright, second one, just like the previous one, this is going to be the maximum lateral area. So, area lateral of the cylinder is going to be, again, this is 2 pi r cylinder times the height of the cylinder. And this is still subject to the same equations that we had before. Now we're going to have to do all sorts of stuff in here. This is going to be fun. Yay! Alright, so then the height of the cylinder, or the radius of the cylinder, are going to have to, again, have this... Alright, let's go the other way this time, just because I don't like fractions. So we're going to go the other way. This is going to be rs squared minus rc squared. So relationship between the two radii is going to be equal to 1/4 hc squared. So then multiply through, this is going to be hc squared is equal to 4 times the quantity, rs squared minus rc squared. Take the square root of both sides. hc is going to be equal to 2 times the square root of rs squared minus rc squared. Alright, so it makes it a little bit nicer in theory. This is then going to be, again, a lateral. It's going to be equal to 2 pi times rc times the quantity twice root rs squared minus rc squared. Alright, so that's 4 pi rc root rs squared minus rc squared. Alright, so this is the area, lateral area of this thing. So then we want ddrc from both sides. So this is dA drc is equal to, here we do the same thing. This is going to require a product rule just like the previous one. So we're going to do 4 pi is just going to be a constant that comes out, and then we're left with product rule here is going to be rc, drc is 1, so that's gone, and then we just have the square root term, so rs squared minus rc squared. And then we're going to add what happens if we leave rc and then take the derivative of the other term. So that's going to be multiplied by 1/2 rs squared minus rc squared raised to the negative 1/2 multiplied by the derivative of the inside. So rs squared derivative is 0 because, again, radius of the sphere is constant. Then we're going to have a negative 2rc. That is going to be multiplied by the chain rule. So take the derivative of the inside stuff, that comes out like that. All right, so we got this equal to 4 pi is going to be the multiplier for all this stuff. And also, we can take a, rs squared minus rc squared raised to the negative 1/2 out, just like we did last time. Rs squared minus rc squared raised to the negative 1/2. This is then going to pull that out of here, which raises the power, because again we're taking a power negative 1/2 and subtracting it out, or factoring it out, which subtracts your exponents. So this is going to be a rs squared minus rc squared, as is. This stuff is all going to be gone. So rs squared minus rc squared raised to the negative 1/2 has been factored out. And then we're left with a 1/2 times a negative 2 is going to be a negative 1. rc, so rc squared. Okay, good. That's reinforcing. So that's going to be, okay. Cool. Just like last time. This is working out pretty much the same. rs squared minus rc squared raised to the negative 1/2. All right, times the quantity rs squared minus 2rc squared equals dA drc, which again has to be equal to 0 since we're maximizing the area, right? We need to make the change in the area 0. So we got a function that's going to go like this. Our area function is going to go like this, and we reach a maximum when its slope is equal to 0. So Hale, when you come back, that's the reason why there's a lot of calculus behind it. I can teach you basic calculus. Look at me giving away knowledge. And I will say, if A level is similar to pre-calculus in the United States, then you're not that far off. It's not going to be like a stretch to give you that information. Come back sometime. I'll let you know. All right. I'm going to keep working on this, but just as a recap, typically on Wednesdays I do my math streams, and on Fridays I do gaming streams. This week I am taking a week off due to other outside stuff and life. Weird, right? And I will likely be gone for this Wednesday, this Friday. That is the 10th and 12th. And then I should be back on the 17th and the 19th for, respectively, math and games. So again, Wednesday math, Friday games. And then like random surprise streams like this if I get user requests that people are like, hey, can you do this? And if I'm not doing anything else, why not, right? So this is one of the things about people like me. We're just excited about math in general. Or our respective fields. All right, so since we want this is again the same stuff as we did last time. Either the 4 pi times the rs squared minus rc squared is raised to the negative 1/2 is equal to 0, or the other stuff is. So again, because of the zero product property, we have this stuff is 0 or this stuff is 0. So then if this stuff is 0, again, this is 4 pi divided by something. equals 0, but you can't do that because otherwise 4 pi would have to be 0. All right, this is kind of the point of algebra, those of you who have never seen this before. If you were to have a over b being some sort of fraction equals 0, the only way that this is actually possible to get a 0 for this particular function, expression, whatever you want to call it, is if you multiply b on both sides. And then here divides out to get 1, and here you get a equals 0. B times 0 is 0. So the only way, sorry, just realized what I did there. All right, so you multiply by b on the left, you multiply by b on the right, and 0 times b is b for any number that we care to think of, and b divided by b is 1 for any number we care to think of except 0. If b were 0, then we don't have a fraction in the first place, and this doesn't work. So a equal... Nope. 0 times b is not b unless b is 0, in which case that's a problem. All right, so a equals 0 times b is 0. So a has to be 0 in order for a fraction to have, in order for a fraction to be equal to 0. A over b. All right, so in this case, again, what we've got is 4 pi divided by this square root stuff. So rs squared minus rc squared. So if this were equal to 0, then this implies, again, that 4 pi is equal to 0, and we know that that's not right. Right? Any constant can't be equal to 0, except 0 itself. This is rs squared minus 2rc squared equals 0. Again, one has to be 0 or the other. And then when you move this over, this is rs squared equals 2rc squared. We wanted to find out the relationship such that rc is in terms of rs. So divide by 2. This is going to be rc squared equals 1/2 rs squared. I am moving stuff around, so apologies if you're not used to it. It's just kind of... I typically put the variable we're looking for on the left as much as possible. And a equals b implies b equals a. So we'll do that too. All right, so r sub c is going to be equal to the square root of 1/2 times the square root of rs squared, which is going to be rs. And again, we're assuming that all of these are positive because they're real distances. So that's how that's going to work. Rc is equal to 1 over the square root of 2 or square root of 1/2 or anything like that times r sub s. This is 0.707. I know that because of trig. We'll talk much more about that if anybody asks any trig questions. So it's about 71-ish% of the size of the sphere. Radius of the cylinder needs to be about 71% of the sphere. Radius of the sphere. I'll get there. All right, and then 3. All right, so for number 3, we wanted to maximize the total surface area for the cylinder, which again, I really hope we don't run into the same problem we did last time, because that's going to be fun. All right, so max total surface area is going to be 2 pi rc squared plus, somebody correct me if I'm wrong here. This is going to be, again, 2 pi rc, which is the circumference of the circle, times the height of the cylinder. man. I really hope this doesn't mess up like the last one did. It shouldn't, because the relationship between the height of the cylinder is different in this one. Alright, anyway. Oh, thought of another way we might be able to do it. Maybe we will come back. Anyway, plug in the height of the cylinder here. Yeah, that's going to be the easiest way to go. So the height of the cylinder is equal to, we have that here, 2 pi rc squared plus 2 pi rc times twice the square root of rs squared minus rc squared. Equals, this is kind of up to you. I don't usually do this. You can factor out a 2 pi rc here. I don't think it's going to help us any, so we'll just keep it as is. 2 pi rc squared plus 4 pi rc square root rs squared minus rc squared. Alright, so that's area total. And then we're going to do ddrc again of both the left and the right. Something like that. Alright, so dA/dRc needs to be 0 in order to maximize. And again, we're going to take the derivative of all this stuff with respect to RC. So we take the derivative, power comes down, makes it 4 pi RC, plus, this is going to be, again, a product rule. So 4 pi RC, we take the derivative, and the rest of it we leave alone. So 4 pi square root rs squared minus rc squared. Alright, and then I'm just going to move it down to the next line. This is going to be 4 pi rc plus 4 pi rc times the derivative of the other stuff, which we did on the other side. So the derivative here was 4 pi rc times 1/2 parentheses rs squared minus rc squared raised to the negative 1/2 times -2, I'm already out of room, okay, times -2 rc. Cool. Just got to remember that that's all strung together. Alright, so we got a 1/2 and a 2 here that are going to divide out, and then we get the negative that's going to come out front. So 0 equals 4 pi RC. Oh, this one's going to be more complicated. That's alright. Plus 4 pi square root rs squared minus rc squared minus 4 pi rc squared, because we got 2 rc's here. This ought to be interesting. Now times the square root. That's in the denominator, so I'm just going to bring it down. Square root of rs squared minus rc squared. Okay, so I'm going to multiply everything through by square root of rs squared minus rc squared, which is going to make this still 0 equals 4 pi rc times the square root of rs squared minus rc squared. This is going to be a plus 4 pi times rs squared minus rc squared. And this is going to be a minus 4 pi rc squared. That's interesting. Okay, so that reinforces. So this is going to be a 4 pi negative 4 pi rc squared and a negative 4 pi rc squared here too. Okay. I'm going to bring all this to the other side. So this is going to be a 8 pi rc squared minus 4 pi rs squared is equal to 4 pi rc square root rs squared minus rc squared. So I took all this stuff that's here and I moved it over to the left-hand side. Okay. So I'm going to divide through by 4 pi because I don't want to deal with that. This isn't proper notation, but whatever, you know. So this is going to be a 2 rc squared. This is going to be a minus rs squared. Okay, that relationship is from somewhere too. We did that earlier. Yeah, it's the negative of this one. That's going to be equal to 0. No, that's not true. Okay, never mind. Don't listen to me. So that only works if we were looking for the maximum lateral area. In this case, we're not. We have a completely different objective. So that's going to be something different. All right, is set equal to 4 pi is gone. This is rc times the square root of rs squared minus rc squared. All right, you're going to love this one. We're going to square both sides. We need to get rid of the square root. So rc squared times rs squared minus rc squared is equal to, this stuff squared is going to be 4 rc to the 4th minus twice 2, so 4 minus 4 rc squared rs squared, okay, plus rs to the 4th. This side's going to be rc squared rs squared minus rc to the 4th. All right, so we can add rc to the 4th. We can add rc to the 4th to both sides. It's going to be 5. You can't see that anymore. All right. Let's just move this. We'll come back to that in a second. All right, we'll just move up. That's fine. So we're going to add RC to the fourth to both sides. And then we're going to subtract RC squared RS squared. And this is going to be 5 RC to the fourth. This is going to be a, this is going to be a negative 5. Let's switch what order this is. RS squared times RC to the, RC squared plus RS to the fourth equals 0. This is in the form of a quadratic. Excuse me. That's kind of gross. Okay. Okay. Let RC squared equal A. RS squared equal B. So this is a 5A squared minus 5AB. BA, whatever you want to do. Nope. Plus B squared, yeah, equals 0. And then we can try to do factorization with this. This is not going to be pretty. So AC factorization is looking for factors of 5 which add to 5. And their signs have to be the same. So that's not going to work. Alright, so we will take quadratic formula of this thing. Alright, so temporarily, if we think of B as just 1 for the moment, which it's not, but we just pretend for the moment. Alright, so just A star, hang with me, is going to be a negative, B is negative 5. In theory, we could also put like B inside of, oh man, I'm using B. I shouldn't do that. The middle term is, in the quadratic, we got negative 5 from the middle term, plus or minus the square root of middle term squared is going to be, again, negative 5 squared, minus 4. First term is 5, and last term is 1. In theory, we could use these b's as part of our terms that we're using throughout this thing, but that's going to be a little gross. So might actually be better. Alright, so if we are trying to find A, and actually A, so that's negative 5b is the middle term. Negative 5b is the middle term. And AC is the last term, b squared. It's a little gross, sorry. Over 5. Twice 5. Alright, 2a. Okay, so this is going to be a equals negative negative is a positive 5b plus or minus square root. This is going to be 25b squared minus 20b squared. Square root of 5 is not too bad. Okay. Over 10. So a is equal to, this is 5b plus or minus square root of 5b squared over 10 is 5b plus or minus root 5 times b over 10 is equal to 5 plus or minus root 5. Over 10 times b. So then this means that a was RC squared. So close. A was RC squared. That was times RS squared, which is B. And then we can say that this is just going to be radius of the cylinder needs to be the square root of that thing. 5 plus or minus root 5. That's nested. I hate those. Over 10 times the radius of the sphere. All right, and then we can also backfill to find height of the cylinder as well, if you got that. Oh no, no. I grabbed it. That was a mistake. Okay. So we wanted to look at what happens if the max total surface area, we have the radius of the cylinder now is this value, just two potential values, which makes it kind of interesting. I guess we could, at this point, have a problem with, I think the negative one is going to cause a problem. So this is going to be 5 plus root 5 divided by 10. Hmm. 5 plus root 5 inside of a square root divided by 10 gets us 27% or so of the size of the sphere. The radius of the cylinder is 27% the size of the radius of the sphere. And then if we do the negative one, it's going to get us 16.6%. So that's interesting. No, okay. So both of those are going to be that's interesting. I don't know about that. So one of the other things that we could do is plot this on like Desmos or something. See what these actually get us for the, we could do the original, probably here, a equals 2 pi x squared plus 4 pi x times the square root of arbitrary constant minus x squared. So let radius of the sphere be 1, for instance. And then we could find the radius of the cylinder based on that. So I'm not above just figuring out what this is by going to a graphing calculator of some kind. Okay, so we got a equals 2 pi x squared plus 4 pi x, not k, times the square root of 1 minus x squared. Okay, so we do have two solutions, and they are not what I got. Hooray. That's not good. Alright, so I must have screwed up somewhere. That's unfortunate. Yeah, so the zeros of this particular function should have been 0.851 times the radius of the sphere, or negative 0.526, which is just not going to count. So the question is, where did I screw up? Alright, so when we took the derivative, this is RC, so it is a variable. It's going to be 4 pi RC plus 4 pi R gets eliminated, and then we're just left with the rest of that. Okay. Here. Alright, so let's take this one step at a time. So now we've got, whatever this is going to be. Sure, y equals, because I don't care. 4 pi x plus 4 pi square root 1 minus x squared plus 4 pi x times half. This guy raised to the negative 1/2. No, I'm not including you on this. I'm not showing it. I'm sorry. It is, I'm just going through each of these steps, though. Alright, 1 minus x squared times negative 2x. Alright, so now, do these match? Yes. Okay, so these zeros are okay. Now let's jump down a bit. What about here? So if we jump down to this line here, I want to make sure that these actually make sense too. We should get the same zeros for this again. So this is going to be 2x squared minus 1, which should be the same as radius of the cylinder is x times the square root of 1 minus x squared. Okay, now I'm still looking for zeros at this point. There we go, the intersection points. Nope, I'm looking for the intersection points between these two, which is still working. Okay. When we get down to the bottom, what about the polynomial? So 5x to the 4th. It's supposed to be plus or minus. Maybe. Alright, so 2x to the, or 5x to the 4th minus 5x squared plus 1. Where are the zeros for this thing? Okay, 2 of them are correct, and 2 of them are just the opposite numbers. So I should be getting that a squared is equal to these two numbers, exactly as they are right now. And yet 5 plus or minus root 5 is not getting me these. So oh, the 10 wasn't underneath the square root. Man. Is that going to do it? Yep, that's going to do it. All right. So, troubleshooting. Very important skill. Yeah, and then the negative version. Yeah, okay. Nope, that's not what I wanted. Okay. All right. So, solutions that actually work in this are when you get a... All right, this is going to be maximized at RC equals giant square root 5 plus the square root of 5 over 10 times RS. It has a minimum at, which again we don't care about, but you want to make sure that you're doing this right. RC equals the square root of the negative square root of 5 minus the square root of 5 all over 10 times the radius of the sphere. Which again, we don't care about this because this is negative and it's the minimum. We want the maximum. But it's worthy to note that this here should be a plus or minus under certain conditions. So because it's under certain conditions, we notice that the maximum for this thing only exists at this particular value. This is approximately 85.065% of RS. So when we have our sphere, let's see, this is half, 3/4, 7/8. So it's like just under this. It's roughly here. Again, on that side, half, 3/4, 7/8, give or take. And this is totally symmetric. Yeah. All right. This sphere should be totally symmetric. So we end up getting something like this. And here the area is maximized, or the total surface area of this particular cylinder is maximized compared to the radius of the sphere, or compared to whatever. If you were to make this any taller of a cylinder, the total surface area would decrease. If you make it any squashier, the total surface area would decrease, if only by a little. Max lateral area. Let's see, this was 71%. So this is what I do with my trig classes, is I look at this and I say, okay, you got sphere. This would be like the unit circle, but I'm usually saying, okay, there's half, there's 3/4, and so like 71% is about there. So we go the other way, half, 3/4, just under. credit my art very much here. I know some of you were impressed, but welcome, Aiden, if you're still here. If not, it's alright. I understand. Alright, alright, we did want to figure out if this was equivalent to number 1. So if we wanted to find the volume, the maximized volume of the cylinder inscribed inside of a sphere, is that going to be equivalent to the maximum area of a rectangle inscribed inside of a circle? So I thought just intuitively that yes might be the answer, but let's actually prove it. So so the area of the rectangle is going to be, in this case, right, if we're looking at this, we can move it potentially across this way or up this way. The relationship between the height and the width of the rectangle ends up being the same as the relationship between x and y on a circle. So if we're looking at this, this is going to be again, center of the circles here, goes out. This is going to be R. This is going to be your Y. This is going to be your X. Nope, it doesn't belong there. Alright, so x squared plus y squared equals r squared, which any good trig student should be able to tell you. Area of the rectangle, not square, area of the rectangle is going to be 2x by 2y. And this relationship exists between x, y, and r. Again, eliminate one of the variables, get r in there instead, because r is going to be a constant. So it doesn't really matter. Y squared is going to be equal to r squared minus x squared, or y equals the square root of r squared minus x squared. And again, only positive in this particular case. So we want all positive values. Alright, so then this is going to be 4xy, or 4x times the square root of r squared minus x squared. Alright, so again, this is intuitively making sense compared to the three-dimensional version, because all a cylinder is and all a sphere is are rotational solids of rotation. So we're doing the same thing to get them. If this was like a sphere and a rectangular prism, this would not work. The intuition would not work. The same, you would definitely not get the same values for them. At least as far as I know. You might. Yeah, I don't think so. But anyway, this gets that. So the area is going to be equal to that. Area of the rectangle equals 4x root r squared minus x squared. And now we want, again, ddx of both sides. Okay, here is going to be, nope, not partial. dx, which we want to be 0 for maximizing the area, is equal to, again here, this is going to be product rule between 4x, which is going to be just 4 square roots of r squared minus x squared, plus 4x times 1/2 r squared minus x squared raised to the negative 1/2 times a negative 2x. Multiply this through, or multiply it over. This is 4 square roots of r squared minus x squared. And this is going to be 2 divided by 2 is going to be 1. That negative pops up front, so minus 4 x squared times r squared minus x squared raised to the negative 1/2. Again, this is 0. Multiply through by this stuff raised to the negative 1/2. No, multiply by this stuff raised to the positive 1/2 power. Or factor out the negative exponent version. And this is going to end up being 0 here. This is 4 times r squared minus x squared minus 4x squared. Divide both things by 4. 0 equals r squared minus x squared minus x squared. R squared minus 2x squared equals 0. This is 2x squared equals r squared. So x squared equals 1/2 r squared. We get the same thing. Yep, cool. So x equals square root of 1/2 times the radius. Yep. So the radius of the cylinder, which was x, needed to be the square root of 1/2 times the radius of the sphere, which was, in this case, just r. And then the same thing happens for our y values. This was the height of the cylinder that we had in the previous one. And again, that's just going to end up being, plug that stuff in here. So square root of r squared minus 1/2 r squared. Yeah. Oh. Maybe not. The height's different. Oh no, and the... No, this was the same as the lateral area. Huh. Okay. That... Oh. Yes, that makes sense. No, that makes sense, because it's not going to be the same as... It's not going to be equivalent to 1. It's going to be equivalent to 2. Let's see. What is the height of the cylinder in this case? It's the same... Alright, yeah, this is the same here, so... Yeah, so it's equivalent to 2, not to 1. Alright, square root of 1/2 times r. Yep. Again, over here, that... I gotta stop grabbing things. Twice square root r squared minus rc squared was all this stuff. Here, 1/2 rs squared. So the height of the cylinder was twice, and then here we had square root of 1/2 times RS. Yep. So this is the same. So y is only half as much, so y is the same as the 1/2. It's square root of a half times r sub s. And let's move that out so you can actually see it. Yep. This kind of took a while. Yeah, sometimes this is the problem with related rates, is that they just take a really long time to set them up and then actually do them. Most of the time it's not too bad. Yeah, so this is a typical related rate problem. So there's a spherical balloon. And the volume is increasing. The volume is increasing at a rate of, so you know this is dV dt, 4 cubic feet per second. So if when the radius is r, we have 4 cubic feet per second as the change in the volume. At what rate is its surface area increasing? So volume, we don't want the volume, in fact. No, we need the volume because we need to get this stuff. So the volume is 4/3 pi r cubed. The surface area is 4 pi r squared. These are formulae that I just kind of know. But interestingly enough, if you look at the volume for the sphere versus its surface area, you'll probably notice that surface area is the derivative of volume. So, interestingly enough, they're actually giving us what the surface area is at that particular time. It's not going to help, but because we actually need the other rate in there to do anything with it. So we want dV dt, or we have dV dt. So here we have to take the derivative of this stuff. So dV dt is equal to 4/3. You bring the 3 down, it multiplies. So we got 12/3, or 4 pi r squared is equal to 4. So then here, this divides out. We get 1 is equal to pi r squared, or r squared is equal to 1 over pi, or r is equal to 1 over root pi. So then we're looking at, all right, what's the surface area? And at what rate is the surface area increasing? So here we'd actually want the derivative of this thing. dSA dt is going to be equal to oh shoot. Nope. Nope. I forgot a term. Woo! I gotta back it up. I mean, it doesn't really change anything because we're gonna pretty much do the same thing. But this is really important. All right, so technically, all right, because we're taking the derivative with respect to t, we also then need a dr/dt term. That's what I'm forgetting. Okay, so dv dt is 4, which equals 4 pi r squared times dr dt. Okay, now we need to solve for dr dt because over here, when we take the derivative, dsa dt, this is going to be equal to, take the derivative here, again, power comes down, makes it 8 pi r times dr dt. Now we need this. All right, anyway. So we divide out 4 pi r squared. And it doesn't matter that we don't know what r is. That's going to work itself out in the end. Dr dt equals, we got 4 divided by 4 is going to be 1 in both places. So dr dt is 1 over pi r squared. Interestingly enough, this is 1 over the cross-sectional area of what we have. So, yeah, cross-sectional area of what is here for the spherical balloon is going to end up being our speed at which the radius is increasing. Naturally, as the balloon gets bigger, it's going to start slowing down because the constant volume increase is going to cause the balloon to fill mostly on the inside, and there's more volume to fill when you're bigger. So when your balloon's bigger. So in this particular case, right, as we increase our volume, the radius's rate of change will start decreasing. All right, dr dt equals 1 over pi r squared. This then comes over here, and we get 8 pi r times 1 over pi r squared. dsa dt equals, here we got a pi out of both places. Here we got an r in both places, so we can divide out 1 here for that one. And this makes 8 divided by r. So the surface area will increase per unit time as 8 divided by whatever the radius is at that moment. And this is going to be in square feet per second. All right, it's 1 o'clock local time, so I'm probably going to give up at this point. At any rate, Soul Reaver, thank you for posting all of those. Anybody who wants to check out his channel, if you have like basic math questions all the way up through like you're starting into calculus, he's on related rate, so that's like halfway through the class. That's good stuff. So if you have any like derivative type questions, he could be able to handle that too. So his handle is SoulReaver09. here on Twitch. You can go check him out. And let's see. Thank you for coming to the stream at any point, whether that's live or video on demand. Thank you for coming to the VOD, and I will again be not streaming this next week. Who knows? I might do another surprise stream tomorrow. I have to be somewhere on Wednesday, and so I'm not going to be streaming that night. And I'm not going to be streaming on Friday night because I'm going to be busy with other stuff. So, hope you all have a good week. Again, if I'm here later, great. And if not, I will see you hopefully on the 17th. So that's going to be my next scheduled math stream is going to be Wednesday the 17th, 9 p.m. local Eastern, and that is 6 p.m. Pacific or 0200 UTC. So if anybody is interested in that, I guess that's technically Thursday morning, UTC or beyond. And I am going to go ahead and raid, if we can, if there's anybody else here. Of course. Yeah, okay, there we go. Stream manager. Alright, here we go. Should have had this up. Hey, Kyle GA, welcome. And Kemem. I didn't actually see your names anywhere, so that's cool. You're here. Thank you. I don't think I'm seeing anybody that I know who's on, which is a shame. Alright, so we got like gaming type people. They're kind of big. Let's see. Let's do Dev. He's a nice guy. Alright. So we're going to go say hi to Dev. He's a good guy. He's doing 7 Days to Die right now, so it's zombie apocalypse type thing. If that's not your deal, have a good one. I'll see you later. And thank you for coming. I am Obi-Wan Pez. This is N Simplex Pachinko. Please go ahead and check out my other stuff if you're interested. If not, see you around.